Hey guys, welcome back to the part 2 implementation of the Monte Carlo reinforcement learning algorithm. We're going to be implementing it onto the game of Blackjack, and if you haven't seen the part 1 series, you can either click the video link that is up on the screen right now, or you can check out the description box down below and the video should be linked there as well. Without further ado, like always, let's get right into the code. Alright, so let's get right into it. In the last episode, we basically covered how to create the generate episode function, and today we're going to be basically defining the function for getting the epsilon-greedy policy. But before we do that, let's see if I don't know why it's doing okay. Expected. Oh my god. Okay, there we go. Perfect. I think that should work. Epsilon-greedy. All right, yeah, we can't really do that yet. So let us first define the policy action. Epsilon-greedy policy. So let's see what we have to take in. And by the way, like I love defining the functions in this manner because once I get to the particular part of the program where I need to call my functions, I know exactly what I have to put in for my parameters. If I define my functions first before even like starting the program, then like I can't really remember what I have to particularly put in, so it becomes like pretty hard. So now I know, all right, so I'm gonna have to take my action, I'm gonna have to put in the Q, I'm gonna have to put in the state, and I'm also gonna have to put in epsilon. And I'm just gonna see why I've been, okay. So let's quickly go over how we're going to be defining the policy. So the policy, this is basically the policy. So what basically this is saying for the epsilon-greedy strategy, we're going to take a random action epsilon amount of the time. And A of S basically means the action that we can take given a particular state that we're in. And the double brackets is the number of actions that we can take. So essentially, all of this complicated term, all of this complicated symbol, this is just 2 because we have 2 actions in every single state, right? So we're just doing epsilon divided by 2 because we're going to have to evenly distribute the probabilities into all of our actions. So epsilon amount of the time, we're going to be choosing a random action. And so that means basically to complete the, to add up the probabilities, 1 minus epsilon amount at a time, we're going to be choosing the action that maximizes the key value. So if you remember from basically whether my article or from just learning MC methods itself, for value-based algorithms, we're going to be taking the argmax of the Q function in order to get the policy. So I'll just quickly explain it. So we're going to take the argmax of the Q function because the Q function of a given state, we have, remember, 2 actions, and we're just going to select the action that has the highest value, because whichever action has the highest value, that means it has the biggest chance of giving us the biggest reward, the biggest long-term reward. So 1 minus epsilon probability of the time, we're going to be choosing the action that maximizes the Q value. So we're also going to have to add in this additive term, which is again epsilon divided by the number of actions, because we can also choose the most optimal action if we decide to randomly sample a particular state, randomly sample a particular action, right? So for this reason, we can get the most optimal action 1 minus epsilon probability of the time or epsilon probability of the time, because we're going to be, when we do this else statement, we're going to be as well, we have the possibility of getting the most optimal action as well as all the suboptimal actions. All right, so let's see how we're going to be defining this. So first of all, we're going to have to define probabilities, right? So we can just say np.zeros at first. We're going to be defining this as we go. And we need a way to capture the most optimal action. Action is going to be equal to the most optimal action. How are we going to cover? All right, so the most optimal action. So we can see we're passing in Q. So over here, we're going to take in the argmax of the Q of the state. So that's basically the optimal action. So this is either going to be a 0 or a 1. So next we have to consider the suboptimal action. So this is going to basically be the other action because it's suboptimal since it has a lower Q value. So how we can represent this is by doing something like this. We have the optimal action minus 1. All right, so let me explain this. For example, let's say our optimal action is 0. And we do 0 minus 1. That gives us negative 1. If you take the absolute value of that, that means we're going to be getting 1. So whether our action is 1 or 0, the suboptimal action will be the other one. So if our optimal action is, for example, 1, suboptimal action is going to be 0. And by doing the absolute value, it allows us to capture, for example, if our optimal action is 0 and 0 minus 1 is negative 1, we take the absolute value of that and we get 1. So that's one way we can define the suboptimal action. So once we get that, we just want to update our probabilities. Probs optimal action is equal to, so let's go back. So you see the optimal action is 1 minus epsilon plus epsilon divided by the number of actions that we have. So that's 1 minus epsilon plus the epsilon, from the bracket, epsilon divided by 2, right? Yeah. Then we're going to do probs. Probs sub optimal action equal to, this is just epsilon, if you remember it right here, epsilon divided by the number of actions. Yeah, divided by 2. That's essentially it. Now we have defined our probabilities, so all we have to do is choose an action according to the probabilities. Perfect. So action is going to be equal to, so we can just define an np.random.choice p.arrange. So arrange means it's going to basically contain a numpy array of 0 and 1. That's going to constitute of our actions. And in that case, we're going to have to define our probs. There we go. That's perfect. And that's going to give us an action based on the epsilon-greedy probabilities that we just defined. And that's essentially it. We're just going to return the action. So now, once we go back here, we can just click that, bang, bang, and we go here. We're going to choose our action given the epsilon-greedy policy Q state epsilon. Perfect. That should work. Q state epsilon, and everything else here should be defined. Yep. Let's see if it works. Perfect, it works. So let's just quickly check if our yeah. So let's check if our generate function works. Generate, we're going to pass in Q. Yep. Do we haven't defined it. Let's just quickly define this here. Let's just completely do perfect. This is just a tested by the way, and then we can define a random variable, just like a random number for epsilon. Let's just give epsilon 0.7. Generate episode. Perfect, it works. So let me see, I just want to give 1 second. Oh my, okay, there we go. So basically, the first element in the list of the first tuple is basically the state. And then once we are in a particular state, then we take an action. In this case, we took the action number 1, and then we got a reward of 0. We got the reward of 0 because our episode hasn't terminated. This means that we can take another action once we transition into the next state. And for this reason, there's another tuple that was returned to us that's containing the next state action and the reward. So for the next state, as you can see, like we basically go from one state to the next. It's going to be the same state, But in the next state, once we're in the next state, what we do is we choose an action of 0, and whoa, okay, like we hit our sum is actually 1, so this is great. Like we chose to essentially stick in this case, and once we stick, we got a reward of 1, meaning that we won that particular episode against the casino, against the dealer. So that's essentially it. Our generate episode function is working properly, so we can delete this now. Yep. So all of these are working. So let's go back to our Monte Carlo control episode here. So now what we're going to be doing is, let's go back to the pseudocode. So 11. So we're gonna generate episodes, right? So let's call this experience equals to generates episode. What do you have to take in? You have to take in Q and then epsilon. Q and then epsilon, perfect. And once we get our experience, I call this experience because experience just basically states, action, rewards. That's just one way to define that particular trajectory of a particular episode. So we're just calling it experience. And then once we get the episode using the epsilon-greedy policy, we're gonna have to loop over the time steps in that episode. So that's basically what this means. We're looping over the time steps. So what we can do here is that we can choose, first, because we're going to be getting a tuple of states, actions, and rewards, we're going to have to first unzip states, actions, rewards is equal to zip star experience. So what this will do is give us our states, actions, and rewards in separate lists so that we're able to properly represent them. States, actions, rewards, and then we have the experience. That's good. So now we can do is for I state in enumerate states. So we can loop over the time steps in using any variable. So because the length of states, actions, and rewards are going to be the same, we can loop over any of them to basically capture the number of time steps. We're going to be doing states because you'll see later on we're going to be accessing this particular state variable. So once we loop over states, so this is where our update rule comes in. So we're going to have to do Q, the state, and then we're choosing an action. We're choosing the ith action, whichever action that we currently select in. Yeah. Choose state, action. Yep. Whichever action that we selected based on the state, we're choosing that. And then so the update rule basically works like this. We're going to be updating by the same value. So that's plus or equals to. And then we are going to have to take in alpha. So alpha is just a constant term that we're going to be using in order to lead the loss in the direction of the update value and to make it, so to make the Q values more accurate over time. So that's what we're going to be multiplying by alpha, and then we're going to have to do returns. So we didn't define our returns yet. I'll define them a bit later. Q state action I. So, okay, I don't think I explained this clear enough. So we're indexing the ith element in the action because essentially it's a 2-element NumPy array because we have 2 actions. So for the state of, for example, let's say index 0, for the first state, we chose action that index, right? So that's the index that we're going to be selecting in that particular state that we're in, and that's where we're indexing by the ith index in the state that we're getting. So that's essentially our update rule. But the thing is, we don't have our returns defined, so we're gonna have to define our returns. Returns is again g of t, if you remember. So let me quickly go here. All right. Returns, we're going to be discounting our return, right? So this is the equation, g of t. So we're going to have to find a way to sum up the discounts as long as the rewards. So we're going to have to figure out how we can represent the discount factor values raised to the kth power, make that equal to the number of returns, the number of rewards that we have, and get that return for each state in our episode. So let's define discounts is equal to, what we're gonna have to do is, let's do this. Let's do gamma. Did we take in gamma? No, we didn't. We're gonna have to take in gamma as well. And let's set gamma is equal to 1 as like a default variable. And gamma is equal to 1, yeah. Now let's just do it like this, yeah, gamma. We're gonna do gamma I for I in range of the length of the rewards. This is where it gets a bit tricky. We can't just define it as the whole rewards. For example, let's say we have 3 rewards. We just can't define it as 3 rewards because we're gonna have to take into consider for the state 0, state 1, and the state 2. We're gonna have to account the return and the discounts for every single state. So we're gonna have to define the discounts for the current return, for the current basically state that we're in. So essentially, if we're in the second state and we have 3 states in total, then essentially we're gonna have to have 2 discounts, right? So that's where we're defining the discounts in this manner. And then what we can basically do here is that we can now define our returns as the sum of the rewards multiplied. And again, this is going to have to depend on the ith index. So whichever state that we are currently in for a particular episode. So if we're in the second state, we're going to have to consider our rewards from that second state. We cannot consider it from the 0th state because that wouldn't make any sense. Right, and then we're going to be multiplying by the discounts. That should do it. And basically all of this, the returns, is equal to this equation, given the discounted return at a particular time step. And in this case, t, right here, t depends on the ith variable. And again, like, yeah, for I in horizon. Okay, for I in, Yep, makes sense. So this is basically the time step. Instead of calling it k, we're calling it I. And this is how we get the update rule for the Q function. So it's going to loop over a lot of times. At first, it's going to be completely random since the Q value is going to be initialized to 0. And then because we have returns that are defined from a true value, and this true value in this case are the rewards, the Monte Carlo learning is able to converge the most optimal policy using this particular update rule. And this update rule is just basically we manipulate the incremental mean equation in order to get it to this form, and then we just multiply by the constant alpha instead of multiplying by the number of the number of episodes that we looped over, essentially. So again, like, all these derivations are going to be inside the article that I created. So if you do want to get a bit more intuition into how these equations are derived, then you can go basically read my article on that. So yeah, that is it for defining the Q function. So let's go back to our algorithm. And yeah, that is it. So we do have to consider a few more things. All right, so the next thing is we're gonna have to return a policy too, right? So it's saying that we need to return a policy. So in value-based methods, which Monte Carlo control is a value-based reinforcement learning algorithm, the policy is implicit. It is just the argmax of the Q function for that particular state that we're in. So this is how we're going to be defining the policy. We're going to again define it as a dictionary. We're going to take in the state. We're going to take in the np.argmax of the Q value. All right, and then for state, and then Q value in Q.items. That's essentially it. So this is going to give us the state for that particular Q function, and then also the corresponding Q value. And to get the action, well, policy is just mapping a state to action, right? So to get the action for that particular state, we're just taking the argmax of that Q value in order to choose the action that's going to have the highest Q value. So that's essentially the policy. And then we want to actually define one more thing quickly. So we also want to keep track of all the rewards for all episodes. We can define an empty list here because we want to calculate the win rate, and this will help us calculate the win rate. And once we zip out our full rewards, we can just do rewards all episodes dot append reward sum of the rewards. So for example, we want to have make a list where we basically can get all of the rewards that we get for every single episode that we define. So we actually want this to be a numpy array. So numpy array rewards. We also want to rewards. Yeah, perfect. And then once we're done all of that, we can just return our Q, return our policy, and we need to return our rewards all episodes. Yep, that's essentially it. Before we return that, we want to, no, I think that's good enough. Does it work? I really hope it works for state. Yeah. I think I'm forgetting. Yeah, okay. So we need the discounts to be numpy array. I think that should be good enough. See? All right, so let's try it now. These are all of our values. Let's set alpha is equal to 0.03. So 0.03, these are essentially just hyperparameters, right? So these were values that were tested in order to see which one leads us to the optimal policy the fastest, and which actually does lead us to optimal policy. So 0.02 is what's used in the Udacity Nanodegree program. I'm just gonna try to 0.03 and let's see what we get. So again, these are hyperparameters. And now, once we do all of that, we can try calling this Monte Carlo. Perfect. Monte Carlo. So we're going to be returning the Q. We're going to be returning the policy. We're going to be returning the rewards all episodes. I think that should be it. Let's see. Alpha is not defined. Oh, there we go. Action is, okay. I see what we did. Action is not defined because it's actions. And is that it? Actions. All right, so one thing that I just quickly forgot to implement is basically, once we do all of these steps, we also want to basically count, in this case, if episode, perfect, episode. Yeah, I basically just forgot to implement this. So this is going to just be a counter when we're training in order to see if our algorithm is actually training. So that's essentially it. You can just copy and paste this, and yeah, so this is going to keep track of where we are, particularly in that training process. Done, 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 and let's run it. Let's see if it's working. Perfect, it is training now. It's going to be training for 1 million episodes, so we're going to come back once the training has finished. Okay, so I think our algorithm has finished training up. 1 million episodes has been done. So now let's just print out Q to see if we got it. Yep, perfect. So this is just default dict. So for each state, it contains a NumPy array that includes the Q values for that particular action. So in this case, for example, the most optimal action to take would be action number 1. So I think that's hit. So yeah, exactly. So when the player sum is 9 and the dealer is showing the value of 1 and the usable ace is false, it would make the most sense to hit in that case rather than to stick. So that's basically all of our Q values. We just do the length of the Q values to see how many we got. 380 states that we visited. All right, perfect. Not 380 states, 380. Yeah. So now let's basically just plot rewards, win rates. Pretty sure that's what the function is called. Rewards all episodes. So this contains all of the rewards that we got in a particular episode, right? So this is just going to plot our win rate to see what's the percentage of time that we actually win in Blackjack as we train all of the episodes. So let's see, num episodes, okay. So num episodes, I think it'll work. Perfect, it worked. Okay, so as you can see, this plot includes a random policy where essentially when we don't implement your optimal policy, we just take random actions with a uniform distribution for like 0 to 1, then we don't really get that good of a policy. Like our win rate is pretty trash. It's around like 25%. But with our optimal policy, which is basically the rewards of all episodes, this means at first it's pretty bad, as you can see. It jumps up because it has the ability to like win super quickly at first, but then it jumps back down. So you can see it like steadily increases over a bit, and then it plateaus around 40%. So that means we achieved our goal. I don't know if it goes to exactly around 42. Maybe you can, but again, like it's really about just playing around with the hyperparameters and seeing which one really works. But essentially that's it. We implemented our Monte Carlo reinforcement learning algorithm with every visit and being at constant alpha, and that's basically it. So we are done coding on our algorithm. So we can also just plot our policy to then compare with the solution policy. All right, so let's see. This is okay, so let's compare. So this is the solution. This is the most optimal policy. So without usable ace, okay, so without usable ace, if we decide to, so hit is the dark areas, and this is the right side. Yep, so as you can see, it goes from hit, and then most of this area is stick, and then it goes to hit again, so that's looking proper. And with the usable ace, we usually hit most of the time. And yep, hit, and the shape here is looking pretty accurate as well. Again, like this could be improved, like this dark patch shouldn't be here. I mean, this light patch shouldn't be here. By playing around with the parameters and seeing which one works in order to get a better policy. But I think ours is pretty good enough at it, as it goes to, yeah, it gets pretty much close to 40%, which is essentially the optimal policy. And we're going to be playing perfect blackjack most of the time, and that's essentially it. We just coded our agent to play the perfect blackjack in order to maximize the amount of money that we win in playing blackjack. All right, sounds good. See you next time.